Hi, how are you? I wanted to do a tutorial about permutations, combinations, and the multiplication rule just because it's been a while since I've done any sort of statistics. And I was looking at something today, and the question was, if you have 3 dice, what is the chance that you'll throw a 6? And the way that the result came about is that it would be 42% of the time. So basically what was happening is we were viewing it as every time you throw the dice, it's 1 and 6 that you'll get a number of 1 to 6. So in this case, we're just looking at the number 6. So dice 1, 1 and 6 tries, dice 2, 1 and 6 tries, and dice 3, 1 and 6 tries. So I was thinking, okay, then let me just do the basic addition rule. So I sum these guys up, and I'm like, okay, 50% of the time, you should expect to get a 6, since you're throwing 3 dice. But that's not the way they're approaching it. They're doing, let's subtract out the chance that you'll get a 6 to get to the chance that you won't get a 6. And this is counterintuitive to me, so I wanted to actually back it to the result. I'm subtracting out the chance that I'll get a 6. And because these are independent of each other, we're going to use the multiplication rule. Multiply these, and it's 57% of the time that you will not get a 6 after throwing 3 dice. And 1 minus this 57% of the time gives you the percent of the time that you will get a 6, which is 42% of the time if you throw 3 dice. And let's say even if you throw the same dice 3 times, you will end up getting a 6 42% of the time. There is this concept of trying to figure out, if you throw 3 dice, what kind of combinations can you get when you throw 3 dice? So you can throw them one at a time and get a set of 3, or you can throw them at once and get a combination. You use the multiplication rule when your numbers can repeat. And what I mean by that is you could get a 1, 1, or a 1. You could get a 1, 1, or a 2. You could get a 2, 2, or a 1. You can get a 2, 2, or a 4. And these are multiplication. And this is the multiplication approach. So basically what that says is the number of different combinations that you can get out of 3 dice is 6 to the power of 3, or you end up counting this graph here, and that's what I'm basically doing here. I'm using literally a counting technique. I'm actually counting the combinations because this 42% does not come intuitively. Or this 42 times the different number of combinations you can get, or 91 times out of 216 possible combinations and attempts in throws, you will end up getting at least a 6. Or at least a 5, or at least a 4. So just to give you an idea, this 216, you can back into by adding up. If you can see here, the way I've done it is one combination, another combination, another combination. Maybe it's easier to see them here. You can throw a 1, 4, and a 2. At L6, you can throw a 1, 4, and a 3. And I've basically done dice 1 up here, dice 2, and dice 3 to try and capture all the different possible combinations, and then I sum them up to respective totals, and then I just do well, count if these totals. If you throw 3 dice, if the sum of those dice is a 3, if the sum of those dice is a 4. So for instance here, I'm saying if the sum of throwing the 3 of them is a 9, which I do with a count if, and I could do combos like 1, 2, and 6. Or I could do another combo here and 15. Like the first dice is a 3, the second dice is a 1, and the third I got a 5. So you can get your 216 in this manner by the multiplication rule, which is 3 sets of 6, or 6 to the power of 3. Or I just ended up counting the number of ways by looking at dice 1, dice 2, and hold these to be true, and then summing up. Okay, if I throw a 1 and a 1, the third would be a 1, or a 2, or a 3, or a 4, or a 5, or a 6. So I sum all these guys up to be the count of attempts, say, or the count of combinations. And then you get into play with the rule of permutation and combination. And this is how we usually approach them. If you look at around F4, you see, in this case, it would be the number of assets in a portfolio, and you're trying to figure out, okay, well, how many pair of assets can I get? Different pair of assets can I get? In this case, you would use n times n minus 1 divided by 2 to try and get to the covariance, because you need that to figure out your portfolio variance. So it is the combination of pairs, and they start increasing. Like if you're using just 2 assets, you basically have 1 covariance or 1 pair. And it would be this here. So 1 pair, you could have Apple stock and Microsoft with a covariance, or Microsoft and Apple, and they're both the same. So you basically have 1 pair. If you end up throwing in Lockheed Martin, say, and now we have 3 assets, you would play them as 1 and 2, covariance 1 and 3, and then 3 and 2. And have 3 covariance. And it doesn't matter if you have a 2 and a 1, a 3 and a 1, or a 2 and a 3. So you're not looking at this logic at all. You're only looking at this logic, which is referred to, because none of them do repeat, it's referred to as a permutation. And what I mean by no repeats, and just really quickly to tell you, a combination then would be order doesn't matter. And what I mean by that is, let's say we have 3 assets and we're doing 1, 2, 3, or we're doing 1, 3, 2. This and this for a permutation would matter. For a combination, you can get rid of it, because it doesn't matter then if you get a 3, a 2, or a 1. This would be the same result, basically, if you're approaching it using combinations. Unlike if you're approaching it using permutations. So what I want to touch on here, the difference between the multiplication rule and a permutation. I'm not even going to get into the addition rule. Just trying to get back to, what is this, 42%, or 91 tries out of throwing 3 dice 216 times. So I'll get 216 different combinations, and 42% of that time, or 91 times, I'll end up getting the number 6. And the way I backed into it is, I drew out the graph here where, let's say dice 1, I get a 1, and then I get another 1. Or I get a 1 and I get a 2. I get a 1 and I get a 3. So every time I get a 1 or a 2, and then a 2 and a 1, this is included in the permutation calculation. What's not included in the permutation calculation are equal signs. So the 1 and the 1, the 2 and the 2, the 3 and the 3, these are not included. And what I mean by that is, just say I'm playing around with 2 dice. If I threw those 2 dice, I would get 36 different sets of combinations if I'm using the multiplication rule. So I'll basically just do 6 times 6. And I'll get 36 combinations. But if I'm using the permutation rule, I'll end up getting 30 combinations. This is because I do not include like pairs. I won't include the 1, I won't include the 2, and I won't include the 3, 3, the 4, 4, because they can never repeat, and that's the difference. For instance, if I want to then include back into the combination result, which is here in this one, I'm doing permutation, so 6 factorial, this is a permutation calc, 6 factorial, and then 6 minus, I'm selecting 2 items from a set of 6 items. I'm selecting 2 out of 6, the way I'm backing into it, and it results into, this is the 2 permutation, it results, that's the denominator, 6 minus 2, and then permutation 4, 4, 3, 2, 1. I get numerator 720, denominator 24, equals 30. Now this 30 is not 36 precisely because the permutation is not capturing the 1, 1, the 2, 2, 3, 3, etc. But if I get back into a combo, and in this case, the denominator becomes this 24, this is a combination, so this 24 times, again, the 2 factorial, and that's the difference between a permutation and a combination. You add times over here where the F5 is, times the pair, so I multiply this times 2 factorial. Basically because 2 factorial is 2 times 1 equals 2. And then I divide the numerator by the denominator, so I get 15. And the reason that's 15 and not 30 is because not only am I subtracting out these like times, the 1, 1, the 2, 2, or rather not including it in my count, but when I look at a 1, 2, and then I see it exist again, over here is a 2, 1, I strip this out and do not include anything that's like kind. And that's how I get back to 15 combinations as opposed to 30 combinations as opposed to 36 combinations using the multiplication rule. I really wanted to count out, okay, how do I get back to the 216 combinations, and especially, how do I get back to, out of 216 times that I throw the dice, I am going to get 91 times of the time I'm going to throw a 6. And because these are independent of each other, that also means 91 times out of throwing 3 dice, I'm going to get a 5, or I'm going to get a 4 or a 2. And you can see this because, I could just take the mathematics for its face value, which again is if I throw a 6, or if I throw a 1 out of 6 times, throwing that 1 dice, I'm going to get that number. So here's my dice 1, my dice 2, my dice 3. And I naturally just want to sum it up and say, okay, 50% of the time, if I'm playing around with 3 dice, I'm going to get a number. But that's not the mathematics. That's not the way you would see it taught. You'll see something like 5 out of 6 times, you will not get the number you want to throw. 5 out of 6, 5 out of 6, 5 out of 6. And then you multiply this times this times this, the multiplication rule. The number of attempts you'll get not getting your number out of 100% of your attempts. So 42% you will end up getting your number, which in this case is 91 times out of 216 attempts. 216 individual possibilities you will be able to get at least the number 6. 91 for 42% of the time. So how does that come about? Because it's not very intuitive. And this is how you can back into your number. If you look here, you could throw a 1, 1, or a 1. A 1, 1, or a 2. A 1, 1, or a 3. So the way we're perceiving it is, this is how we're going to count. Out of having your first dice and your second dice be these pair combinations, out of 1, 2, 3, 4, 5, 6 times, 1 time, you're going to get it 6. If you have these type of combos. So we're saying here this is 5, and then out of this pair, 1, 2, 3, you keep getting a 6, right? So this is a 5, and this you continuously for 6 attempts get a 6. So 5 out of these throws, out of these 30 throws, 5, and then we'll just go up to this 5, not including this 6 because the 6 is here, and I'm going to count this in its own individual line. So 7, 8, 9, 10, 11. So 11 times, every time leading from starting this combination, 1, starting this combination, 2, starting this combination, 3. Okay. 11 times, every single approach until we get to starting the 6th combination. So we know 11, 11, 11, 11, and 11, or 11 times 5 will give us 55. Then, every time we get a 6 here, it counts. So 1, 2, 3, 4. As long as you're throwing a 6 and a 1, a 6 and a 2 with dice 1 and 2, this counts as at least 6. So we're basically saying 6 times 5 over here, 6 times 5, which is 30, and then another 6. or 36? 6 times 6. That's 91. Times in these individual combinations, you can have a 6. And I wanted just to have the ability to back into 42% out of 216 individual combinations. I actually can count 91 possible times that I would get a 6 in one of my combinations. One last thing I wanted to show you is naturally the way I wanted to approach it is use the multiplication at the beginning. So what I did over here is multiply 1 digit 6, like I'm expecting to get a 6 my first attempt, my second attempt, and my third attempt. But I didn't account for the fact that I'm using a reset and that I can repeat. So I ended up using a multiplication. But then taking this multiplication, so I'm basically saying less than 1% of the time I'm going to get a 6. And taking this logic using 3 sets actually gives me the number 1. And I wanted to show you that this is one of the numbers that comes out, and I really wasn't expecting it. I mean, if I did, again, 1 divided by 6, I get to them this way, and multiply it by the total possible values, and get 1.6. I don't know if that's significant. This is trying to find a pattern and a little bit more numerology, but I found it interesting that if I'm playing with 3s and I have a total bucket here or 100% here, I'm able to get back to a 1, and that starts becoming this digital concept or 1s and zeros and probability. You have these axioms where the total has to be 1. So I thought that was kind of interesting. I don't know what I'm going to do with that, but if somebody else is interested in it, it's kind of something else to be able to back into. How can you get 1 attempt or the number 1 out of the total combination? And it looks like you could do it if you take 1 and 6 and multiply it by itself. Anyway, I hope this helps a little for anyone looking into combinations, permutations, and multiplication rule. And just something I'm going to read directly out of the math book. It's a finite mathematics textbook by Rowe. One way to tell is, first off, how many sets do you have? And in our case, we have 2 sets or 3 sets, 1, 2, 3. 3 individual things that can repeat, and that's the thing that's important. How many sets do you have? If you have more than 1 set, then don't even bother trying to use combinations and permutations. And again, these are the values. So more than 1 set, don't bother using these. More than 1 set, don't bother using these. If you don't have more than 1 set, for instance, if it's 1 population or 1 set of teachers in a school or a bucket of stocks in a portfolio, this is 1 set. If you don't have more than 1 set, like different portfolios that have maybe similar assets in that, so you just have the 1 portfolio or 1 bucket or 1 population you're looking at, use combination, use permutation, but keep in mind that repetitions allow if you're allowed a repetition, so if you're allowed the number 6 again and again, or the number 5, or the same asset again and again, then use the multiplication rule. If you cannot repeat, if we say Microsoft and Microsoft instead of Microsoft and Apple, if you cannot repeat, like Apple and Apple, Microsoft and Microsoft, then use combinations and permutations. And if order doesn't matter, and what I mean by that is if you have Microsoft and Apple or Apple and Microsoft, then you can use a combination, which means if one exists, if you have Apple and Microsoft and Apple, then get rid of one, because only one matters. In that case, you're only counting one. Otherwise, the order does matter. Did you get a 1 and a 2 and a 2 and a 1? You keep those in your count, as we did here for a permutation, but you're going to exclude any duplicates, any 1s and 1s, 2s and 2s, 3s and 3s for permutations. You're going to exclude duplicates for permutations and combinations, and for combinations, you're also going to exclude, if you have a 1 and a 4 here, you're not going to also count it here. You're going to remove it because as far as you're concerned, those are the same thing. Okay, I hope this is helpful, and it's mainly just for me down the line to try and remember some of this probability in math, because believe it or not, there's going to be times when you're looking for randomness, when you need to explain these kind of probabilities, and this does not come intuitively. I would have naturally thought 50% of the time you're going to end up getting your number if you're throwing 3 of them. But apparently not. Apparently it's 42% of the time. And being able to visualize that, and then being able to play around with, okay, what was a permutation, a combination, the multiplication, when do I use that? Why even if I'm playing with 2 pair, the multiplication rule will give me 36, and then I'm getting something over here where I'm getting either a 30 or a 15, depending whether it's a permutation or a combination, and just keep it simple with 2 pairs of dice. To try to visualize the difference and consolidate the difference between the sort of pairs you can get and what each is trying to capture. And maybe that will help assist in combining things or categorizing things. You can find some of the things that I do under jazzfin.com. It's mainly administrative automation, but we also do videos with certain tutorials for materials. So please reach out if you're interested. Leave a comment as well, and any feedback is totally welcome.